about quantum SOS and stuff.
Thanks, Mark. So yes, I'm going to tell you about quantum entanglement, sum of squares, and the Lagrange conjecture. And this is joint work with Boaz Barak from Harvard and David Streuer from Cornell University, who was at the institute this year. So other than me, the other two authors also have a deep Princeton connection. So this talk in total has like a large Princeton footprint here. The title is intentionally chosen to be a bag of words, and part of my job today is to convince you that there is a meaningful relationship between the words appearing in the title, and you know that relationship is worth exploring. So let me start with a full disclosure. This is going to be a algorithm talk. So the main result will be a fast algorithm for a certain algorithmic problem. Let me start by describing the problem. I'm going to call it the low rank matrix in a subspace problem. I'm going to tell you why we should care about this question in a bit, but hopefully like the description will convince you that it's a clean algorithmic question that could be interesting in its own right. So the input to this question is a linear subspace W of n by n matrices. Okay, so you can over the reals. So you can think of this subspace as specified by, let's say, giving a projector to it, or let's say all the linear equations that every matrix in this subspace will satisfy. Okay, you're given the promise. So I'm stating it as a promise problem. This is not the only way to do it, but for today I'll stick to it. You're given the promise that there is a rank 1 matrix described by unit vectors u and v, such that uv transposed is contained inside the subspace W. Okay, and your goal is to recover some rank 1 matrix described by unit vectors x and y, such that xy transposed when projected to the subspace W is almost all of its norm. Okay, so this almost all I'm going to measure with respect to the Frobenius norm of the matrix. It's a natural norm that arises by thinking of the matrix n by n matrix as an n square dimensional vector and taking its Euclidean norm. Okay, so in other words, the problem is to find a rank 1 matrix contained inside a subspace W, given the promise that the problem is to find a rank 1 matrix which is close to the subspace W, given the promise that there is one which is completely contained inside it. Okay, great. So I don't expect you to have intuition about how hard or how easy this problem is at the outset, but one thing I can observe immediately. Okay, let's fix epsilon to be some 0.01 so that I don't have to carry around a extra parameter. Now I can take a fine enough constant like epsilon being constant, epsilon net of a unit sphere in n dimensions, and go over all possible pairs of vectors in this net and check if the rank 1 matrix defined by the pair, you know, satisfies the projection large condition. So this checking is efficient. The net is exponential size, which means that this brute force type procedure would run in 2 to the O of n time. Okay, so the brute force running time for this algorithm is 2 to the O of n, and we want to understand if we can beat this, you know, guarantee. The main result of this talk is going to be a 2 to the root n time algorithm up to some polylog factors in the exponent to solve this question. Okay, this algorithm will be obtained by rounding a solution to a certain convex relaxation, which will be the sum of squares relaxation, and I'm going to explain all of these terms to you later on in the talk. Okay, but before, let me throw out a couple buzzwords for you to look out for, and these will also be the main takeaways from the talk. Okay, one is this idea of using low degree polynomial reweighting in order to round solutions to higher round sum of squares. Okay, so basically this will be a huge semi-definite program, bigger than the kind of SDPs that you've seen before, and what we want to do is round a solution to it, and this idea of low degree polynomial reweightings that I'll explain in the talk would be one general kind of principle that you could use to construct such a rounding procedure. Okay, in the context of this low rank matrix in a subspace problem, when we want to analyze this low degree polynomial reweighting and in fact construct it, it turns out that somewhat surprisingly we can rely on the tools that have been used to prove upper bounds on the Lagrange conjecture from communication complexity. Okay, so this connection between analyzing polynomial reweightings and the techniques in this Lagrange conjecture like stuff would be actually useful to us. Okay, great. So with that extended title slide, I can now go on and tell you why you should care about this question, the low rank matrix in a subspace problem. Okay. So there is a straightforward quantum information problem that this question captures, but today let me try to motivate it from more classical perspective. Okay. Great. So what I want to do is define a skeleton of a problem that you would immediately see is satisfied by the question I wrote on the first slide, the low rank matrix in a subspace question. Okay. And then tell you a couple of examples of perhaps your favorite problems that fall into the same category. Okay. So I'm going to call this the structured vector in a subspace problem. Okay. Input here is a linear subspace of R to the n. Okay. Your promise that there is a structured vector V contained inside this subspace V. Okay. And this structure is intentionally a placeholder. I'm going to replace it by various things in order to get new problems. Okay. And the goal is to find a structured vector W, let's say unit norm, such that if I project this vector W to the subspace V, then it's almost all of it in the same sense that before, the Frobenius norm or the 2 norm here. Okay. So this may appear like some crazy abstraction to you, but let me give you a couple examples as I promised. I want to claim that max cut is a question that hopefully is familiar to all of us, is actually a question of the same type. Okay. In this case in particular, the structure is Booleanity, the 0 1ness of the vector, like every entry of the vector has to be 0 or 1, and here I'm not normalizing. And the subspace actually comes from the graph. It's actually going to be the eigenspace, it is going to be the span of the eigenvectors of the Laplacian matrix of the graph corresponding to the eigenvalues which are bigger than 1 minus epsilon in a normalized setting. Okay, so let me briefly explain to you why this is true, and in some sense this is not really the main point, but let me just tell you a hint at how this comes about. So almost all of us know that max cut can be written as the problem of maximizing the quadratic form of the Laplacian matrix of the graph, okay, on Boolean valued vectors, so 0 1 valued vectors. And the reason is that for any 0 1 vector we can think of it as the set of vertices, and then x transpose Lx actually just computes the size of the cut defined by the vertices. So maximizing this problem is same as computing the max cut in the graph G. Okay. And now if the max cut is, let's say, 1 minus epsilon fraction of the edges, the size of the max cut, then what you can argue is that the optimal cut, like the indicator vector of the optimal cut, is going to be almost completely contained inside the span of the eigenvectors of the Laplacian with eigenvalues bigger than 1 minus O of epsilon. Okay. So in particular you can basically think of this question as trying to find a 0 1 valued vector which is close to the subspace defined by the span of the eigenvectors corresponding to eigenvalues bigger than 1 minus O of epsilon. Okay. A similar question is the so-called small set expansion problem. Perhaps this is maybe less known than max cut, but this is a close variant of the famous unique games problem. And analogous to the unique games conjecture, there is a hardness hypothesis for the small set expansion, which is called the small set expansion hypothesis, which was developed by David Steurer and Prasad Raghavendra when they were here. And in this case, basically, so let me in fact describe this problem briefly to you again. We all know the question of finding a non-expanding set in a graph. Okay. Given a graph, find me a set so that the number of edges that go out of it compared to the maximum possible number of edges that could be there in the graph is minimized. Okay. Now this problem, especially when the expansion coefficient is a constant, is sort of easy to solve using the so-called Cheeger's inequality. Okay. The small set expansion is a variant of this the problem of finding non-expanding set with the additional restriction that the set be small. Okay. This time, therefore, you want to find a set of vertices which is sublinear in size, little o of n size set, such that the number of edges appropriately normalized that go out of it are minimized. It turns out that this sparsity condition makes the problem much harder than the expansion problem that we are familiar with, and that's why this is the so-called hard question. But regardless, it falls into the same skeleton as before. This time the structure is sparsity. Okay, and the subspace comes from the top eigenspace or the span of large eigenvectors corresponding to large eigenvalues of the adjacency matrix of the graph. Okay, and the third problem is what I showed you before, and it turns out that it has a name in quantum information. It's called the best separable state problem, and it is precisely what I told you before. It is the problem of finding a vector when looked at as a n cross n matrix has a rank 1 structure. Okay. And the subspace here actually arises out of what is called as a quantum measurement operator. I am not going to define all these terminology here, but basically suffice it to say that just like the subspaces in this max cut and SSE came from some combinatorial input that we think of, Here the subspace comes from a certain input that is natural in quantum information setting. Okay. Now why would we care about this best separable state problem? If you are a quantum information theorist, there are like great reasons to care about it. In particular, the most solid one is this conjecture due to Impagliazzo, Aronson and Moshkowitz from 2014, who showed that if BSS, in fact they conjectured that the best separable state problem, which is basically the low rank matrix in a subspace problem for us, has a quasi polynomial time algorithm. Okay. The reason they conjectured this quasi polynomial upper bound on the problem is because if this is true, it leads to a complexity class collapse. The quantum complexity class QMA2, which is the analog of two prover proof systems in the quantum world, again not going to define it too much, but it's sort of important in that world, collapses to the classical complexity class exponential time. Okay, and this is sort of a question, this is sort of a fundamental question in quantum information, whether QMA2 has an exponential time simulation. And Impagliazzo et al. Basically defined this conjecture in order to show that if this conjecture is true, then this complexity class collapse actually happens.
Is it considered a collapse in the sense that it's surprising?
Yes, actually. So the reason is so surprising in the sense that
the trivial would be next.
Yeah, the trivial bound is next. Yes. And in some sense, this question is sort of an attack on the question of whether QMA is same as QMA2. So QMA is basically the version of QMA is the version of MA, the randomized NP that we think of, where there is a single prover, but the prover can give a quantum state as a proof instead of just a classical string. QMA2 is a version where there are two provers. Of course, in the classical world, two prover system and one prover system is the same, so long as the communication is only one way. But here, the two prover.
I see. What is this communication?
So it's the MA, right? In the quantum world, however, the two prover system actually makes more sense because you can add the additional restriction that the two provers be unentangled. So this is a way to restrict the cheating ability of the provers, and you could conjecture that this makes the proof system more powerful, given that the provers are the ability to cheat is restricted. So you would think that it's a bigger class. QMA is in exponential time. And the question is QMA2 also in exponential time? This would be somewhat surprising in the sense that even going to unentangle two provers does not add to the power of the single prover proof system. But regardless, I think there are at least quite a few people who would think that this is true. In particular, like Scott Aronson would conjecture that this is true. Great. But again, that's
the upper bound is what in the BSS?
2 to the n.
2 to the n.
So that's the problem, and you can basically just search over a net of the unit sphere, and
You're getting to the square root.
Yeah, so that the result is 2 to the root n time algorithm. Yes. Great. Again, but the quantum version is not really our focus. The question, the only point I want to make is that this best separable state thing that I defined is a basic question in quantum information, and I would basically, if there is some time at the end, I'll tell you more about this part. The problems that I wrote down in this thing at this point appear like just share some common thematic structure, this skeleton that I actually wrote down here, but it turns out that there is a more than just thematic connection between these problems. In fact, just to tell you one instance, I'm not a quantum person. The reason we were looking at, the reason basically we got into this project was basically trying to get a faster algorithm for the small set expansion problem. So we wanted to improve upon Sanjeev, Boaz and David's work, which gave a sub-exponential time algorithm for the small set expansion problem, and we had some candidate rounding. It turned out that our rounding broke down for various reasons for small set expansion, but it succeeded for best separable state. So basically, and okay, of course, you don't have to take our word for it, but there are like deeper connections that we know between the approaches to solve the problems that I wrote down on this slide. And I can talk more about it offline. Okay, so that's sort of my rough pitch for why you should care about the low rank matrix in a subspace question today. Let me tell you a little bit about what's known so that we can place the result in context. Okay, so it turns out that if here I am allowing an error of 0.01, if I make this error actually decreasing with the dimension, let's say I make this 1 over n. In other words, let's say I want a rank 1 matrix which is 1 minus 1 over n close to the subspace, then this problem becomes NP hard. Okay, and this follows from a work of Gurwitz and later by Blyer and Tapp. Okay, so we are going to look at the constant regime where this NP hardness potentially doesn't apply, but it turns out that when this error here is constant, which is the setting we are going to look at, there is a quasi-polynomial lower bound, okay, due to Haro and Montanaro, and this is assuming the exponential time hypothesis, which basically says that 3-sat requires 2 to the theta n time to solve. Okay, so if 3-sat requires whatever we conjecture as the right time bound, then there is no better algorithm for this problem than quasi-polynomial. Remember that that's also the conjecture that Impartliazo et al. Made. Okay. For some special kind of subspaces that arise out of some kind of measurement some special kind of measurement operators in quantum information, it turns out that we can in fact prove a quasi-polynomial upper bound also. Okay, and then this is a result due to Brendau, Christiandel and Yard, who analyze a sum of squares based algorithm due to Doherty, Perillo and Spedalieri. It's not the same kind of formulation that we're going to look at today. But basically the message of this slide is that there is a quasi-polynomial lower bound, so that's basically best what we can hope to do. And in general, for general subspaces, there is no better than the brute force 2 to the n time algorithm that we talked about. Okay, and therefore that sort of motivates the main result of this talk, that we're going to basically give a 2 to the root n time algorithm for solving this problem. And in the new language, we can basically say that this BSS problem has some 2 to the root n algorithm. Nothing new in this slide. I already showed you this before. Just placing it in context now. Okay, great. So moving on, I'm going to tell you a little bit about how the algorithm works and how we analyze it. For this purpose, I'm going to remove another piece of extra notation that I need to carry. So instead of looking at asymmetric rank 1 matrices like UV transposed and XY transpose, we're just going to make Y equals X. Okay, I'm just going to go to the symmetric version of the problem where rank 1 matrix is defined by a single vector instead of a pair of vectors. Okay. This doesn't change anything, but just is less clutter for me to carry around on slides. Great. So now I'm going to describe the algorithm to you. As I said before, the algorithm is going to be a convex relaxation followed by a rounding algorithm. And we are in very much charted territory here. Okay. If you've taken even a single course in approximation algorithm design, then you know what kind of strategy we can follow here almost as a template, right? We start with a certain formulation for the problem. Okay, it could potentially be non-convex in general, because these are NP-hard problems. We will start with a non-convex formulation in general. Okay, so here the formulation is really simple. Remember that we want to find a rank 1 matrix which is inside the subspace W, right? We said that the rank 1 matrix is defined by a single vector X. Okay, we wanted this to be a unit vector, so we add the constraint that sum xi square equals 1, and we want that XX transpose live in the subspace W. The other way of putting it is that if I project XX transpose, the rank 1 matrix, to the orthogonal complement of the subspace W, let's say W perp, then this projection is 0, right? So it's easy to see that if any x satisfies the system of equations, by the way, notice that this is a quadratic equation. Pi W perp is a linear operator, it acts on XX transpose, so these are linear equations in XX transpose, therefore there are quadratic equations in X. Okay? So notice that any x that satisfies the system of quadratic equations is going to be going to give us a rank 1 matrix which is in the subspace by just direct construction, right? Of course, if we could solve this problem, many bad or good things will happen depending on how you see it. This problem in general, feasibility problem, has to be hard, right? For example, it captures exactly solving max cut. Great. So what are we going to do? Well, our general methodology is to write a convex relaxation for this system of quadratic equations. They are by themselves they are not convex, so we want to relax it and then basically work with that relaxation instead, right? So let's say these red points are the solution, the x's which satisfy these two equations for a certain w, right? We want to write a convex set. We want to write like a convex relaxation which is defined by a convex set. It's going to be a feasibility program here because we started with the feasibility program. So we want to write some convex set where we want to solve the feasibility problem, and that convex set must contain all the solutions, right? The tightest possible convex set I could choose is basically just the hull of the solutions. Of course, I don't know any of these points. If I did, I would not be doing this. But let's imagine for now that this is the convex hull. Oops. And we would want our convex relaxation, the convex set, to actually contain this convex hull. Okay. So in general, as I said, we don't have a handle on this, so we enlarge it to a different convex set, a larger in general, which we can somehow easily work with, right? So let's say this is the easily nicely describable convex set that contains this hull. Okay. Then what do? Well, we go ahead and solve the problem of feasibility on this convex set. This is an easy problem, we know how to do it. We will find some point inside this big convex set, and then we are faced with the task of rounding. What does rounding ask for? We want to take this point and map it to something which is close to an approximate solution for the problem, right? Now notice that this problem is not convex, which means that convex combinations of solutions is not a solution, so we really want to be close to one of the vertices of this convex polytope here, the inside convex polytope here. Okay, great. So I've done nothing fancy so far, but I just want to point out that this is an approach that perhaps textbooks and algorithm papers would have you believe is how we construct approximation algorithms. Okay, and to tell you why I would disagree with this kind of phrasing of the approach, let me point out the major dilemma that faces that an approximation algorithm designer faces. And the question is, what comes first? Does relaxation come first, or the rounding algorithm comes first? And the point is the following. Usually what you would end up doing when you are actually coming up with the algorithm is you start with some basic relaxation. Okay, then you go and try. You have some candidate rounding. You go and try to analyze the rounding, and at some point you discover that it would be great if I had this particular inequality in my constraints. So you go back and add that inequality, and you continue your analysis. Hopefully in your analysis you would not need too many inequalities, and you would be able to basically throw whatever inequalities you needed to the constraints, and then basically your rounding algorithm will succeed. So really,
very 21st century view.
This is the 21st century view?
Yeah, definitely. I mean, some of these relaxations are around for decades, and then finally were analyzed, or the TSP subtour elimination.
Okay, yes. So there are certainly examples of really hard problems where in some sense
the relaxation was canonical.
Yeah, the relaxation is canonical, but you agree that there are various examples where you could at least retrospectively see that the constraints were added because they had a certain rounding idea. No? Wow, this is a point I never get objections on, but let's take this offline. Okay? Okay, yes, so this is disputed, but yeah, we'll come back to this at the end. Great, but I still want to go on with my version of the story, where I think that somehow your rounding algorithm informs the choice of the relaxation over and above some basic relaxation that you choose. Okay? So in order to compensate this bias towards writing our results in the sequential order I wrote before, let me reverse the order, just to set the balance of things in the universe correct. So in this version, I'm going to design a rounding algorithm first and then develop a relaxation later. Okay? Let me describe what I mean by that. In the first step on the previous slide, what I showed you was that we started from a convex relaxation of this tightest possible convex set that contains the solutions to the polynomial program that I wrote down, right? In this version of things, I basically don't relax it at all. I don't really know what this set is. I don't know how to describe it. But forget about it, I will continue working with this set, okay? I would imagine that there is some oracle that will give me a point inside it, okay? And then I want to solve the rounding problem. I want to take a point inside this tightest possible convex set that I could write down here and round it to a solution, an approximate solution, so nearby a vertex of this convex polytope. Okay? This is what I call the rounding problem, okay? Now, as I said, what we will do is we will look at our rounding algorithm. We will look at the analysis of the rounding algorithm. We will try to find out what constraints that the solutions following this solutions inside this convex cell really satisfy. Which of them did I really need in my analysis of the rounding algorithm? I would go and dive in to find those constraints and basically add only those. Hopefully there will only be few of them. I hopefully didn't need all of the constraints required here. And then I would have an efficient algorithm because I forget about this convex set. I actually just add the constraints I needed. And then my rounding algorithm essentially just works because that's how we designed it. Okay, so this is my favorite view for today, and this is how I'm going to look at the algorithm that we're going to look at today. Okay, so I'm going to describe the rounding algorithm first, and then go do this dumpster diving in order to find the right constraints I used, and then develop the right convex relaxation. Okay, great. So let's do the first step. We wanted to choose the tightest possible convex relaxation. So we want to develop a way to think about what a feasible point in this tightest possible relaxation looks like. Okay? So we said that any point in this hull is actually a convex combination of solutions to these quadratic constraints, right? I'm going to think of them as just a distribution over actual solutions. Just basically a rephrasing or just a different way to look at things. Okay? So a feasible point in this world corresponds to a distribution over actual solutions, right? So let's try to understand how we can look at this point a little bit better. So mu, let's say mu is the probability distribution which is supported over x that satisfy the kind of equation that we want them to satisfy, the solutions, right? Now let me write down a bunch of properties just to understand how this mu looks like. We basically, our goal is to look at this mu and construct a rounding algorithm from it. So let's try to understand what we know about mu in general, okay? So let E be the associated expectation operator to this distribution mu, okay? Let Q be any polynomial where which works on the space that the distribution is defined on. So x is our variable, q is the polynomial in x here, okay? Two of these properties that I've written down here are basically satisfied by any expectation. Here I'm not even going to use in this part that mu was supported over solutions to my polynomial program that I'm looking at here, okay? These are that it is correctly normalized, expectation of 1 is 1, it's trivial. And the second is that if q is a polynomial which is non-negative over the reals, then the expectation of q should also be non-negative. Okay, we all agree with this. Any expectation should satisfy these properties, right? Now let me try to dig up consequences of the fact that mu was supported over solutions to my convex program. So I want to claim that the following properties are a result of this constraint. Look at any polynomial q and multiply it by some xi square minus 1. Okay, any x that satisfies my polynomial equations, over those x's, q times some xi square minus 1 will be 0 because some xi square equals 1, right? Meaning that such a polynomial is pointwise 0 over the support of any distribution mu which is a feasible solution for me. Therefore its expectation should also be 0. Okay, and similarly I can write a constraint corresponding to these set of quadratic equations. Okay, so far so good. Finally I observe that expectation is linear, we all know that, and therefore its behavior is completely specified by describing it on some basis of polynomials. So my favorite basis for today is the monomial basis, and it turns out that expectations of monomials have a name. They are called moments of the distribution. Okay, so this slide basically collects a bunch of simple properties of expectations associated with the distribution mu that will be satisfied for any mu which we are actually going to look at, right? It turns out that the following nice fact holds. For any non-degenerate, okay, up to some non-degeneracy condition, let's say that in fact for example mu is finitely supported, then these conditions in fact characterize such distributions. They are not just properties which are satisfied, they in fact characterize all such distributions. So that's great. But what was our goal? Our goal was to take this distribution mu and construct a rounding algorithm, to get to an approximate solution by looking at mu. Later on I of course have to convert this rounding algorithm into an algorithmic proof because my end goal is an algorithm, right? So there is no hope of doing this if the object which is input to the rounding algorithm is huge in size. To have any hope of converting it into an algorithm later, I better have a rounding algorithm that uses an object which is small in size. Here to specify the distribution, let's say I do it by specifying all the moments, a priori I would have to specify infinitely many parameters, right? So to correct this problem, just to have small input, I'm going to make the first lossy step in this approach, which is I'm going to look at only low degree moments of the distribution mu. Okay? So once I restrict to this, at least, so let's say if the degree is d, then the distribution is described by n to the d parameters, right? Because I'm only going to describe the expectation of degree at most d monomials. Okay? So at least the description of a feasible point now with this loss becomes efficient to describe. A priori you could hope that this basically solves our other question too. We had infinitely many constraints in general that we wrote down on the previous slide that we said characterizes all distributions. It would be great that if I look at just low degree moments, then I can basically drop most of the constraints and the program also becomes small. It turns out that this is not true, unfortunately. On the other hand, at this point we don't care, so we carry on. Okay? Great. So now we reach to the bulk of the proof, which is to take such a low degree moment of a distribution which is supported over solutions and round to an actual solution. Okay? So let me tell you how I'm going to do this. Let me formalize this rounding problem first. The problem, the input to this problem is going to be degree d moments of a distribution supported over solutions to my polynomial program. Okay? So far that's what we've been looking at. This is the input that it's going to get. I'm going to assume that there is some oracle that will give me such a mu. So let's say I have that. my goal is to construct an X star normalized to be a unit vector, so that if I look at the rank 1 matrix defined on X star and I project it to the subspace W, then I get almost all of it back. The same kind of goal that we had, right? This is really what we mean by rounding to an approximate solution. So all of you agree that this is the rounding problem we are looking at, right? Yeah, if there are any questions, please stop me anytime. Okay, great. So that's the rounding problem we are going to look at. And let me introduce the first idea that we will use to solve this problem. And this is the first key idea. That idea is of polynomial reweightings. Okay, so this is the key part of the proof. So let me spend a couple minutes describing the statement of the main claim here, and then tell you a little bit about how to prove it, etc. So the main claim I'm going to make is the following structure theorem, which holds for every distribution over the unit sphere in n dimensions. Okay, the claim I'm going to make is the following: for every distribution mu supported over the unit sphere, there is a polynomial of non-trivially small degree, root n degree, such that p is non-zero and normalized correctly. So expectation of p is 1. Okay, and there is a vector v0 such that if I look at this reweighted covariance matrix of the distribution mu, so remember that if I didn't have this p here, expectation of xx transpose is just the covariance matrix, right? Now I am reweighting this covariance matrix with p of x. The claim is that if I look at this reweighted covariance matrix, and then it is basically well approximated by a rank 1 matrix in the following sense: there is a vector v0 such that if I compute the Frobenius norm of the difference of this rank 1 matrix and this reweighted covariance, then it is smaller than some tiny number times the Frobenius norm of this v0 transpose. Okay, further, p actually can be computed by looking at only degree root n moments of the distribution mu. Okay, remember that the last factor is of course required because I don't really get to look at mu in our setting, right? I only have low degree moments, so I better be able to compute this p by looking at only the low degree moments. And the important part of the claim is that the reweighted covariance matrix is approximately rank 1. Are there any questions about the theorem as such at the moment?
What do you mean by efficiently computable here? Because you can just write all the monomials, right?
Right, but at this point p is I don't know how to, I have to get to p by looking at the low degree moments of the mu distribution, right? It could be that the procedure that computes each of the coefficients could be not efficient. You could at this point it's also okay to forget efficiency, but basically we definitely require that p be function of just degree root and moments of the distribution mu. That better be true.
But x transpose is a real number.
X transpose is a rank 1 matrix. X is a vector.
So that's a rank 1 matrix, and then px is what?
So x was a vector, right?
Yeah.
P of x is a polynomial in x.
Is a number.
So it's a scalar. Yes. So we are reweighting. So like if in general if we were to compute covariance, your p will not be there, or it would be 1 for example, and we will be computing expectation of xx transposed.
Okay.
Right? What I'm saying is that reweight the sample x by p of x. And the claim is that there is a reweighting with a low degree polynomial, root n degree polynomial, that makes the covariance matrix approximately rank 1.
Is this non-negative?
That's a great question. We don't need p to be non-negative, but the p that we are going to produce today is going to be non-negative. So in particular, this will also be a covariance matrix of some distribution.
Do you know if this is the best you can hope for?
Say that again?
Do you know if this is the best?
For this structure theorem?
Mm-hmm.
No.
And if you insist on positive, then it's more or less Lagrange, right?
If so, let's put it this way: if p is a square, then it is Lagrange and root n is tight.
Yeah, because Lagrange is known to be false if you don't
For non-Boolean.
with the Boolean matrix.
Yes.
But
This version, I don't know why. I don't know a reason for it to be false.
but this version is not killed by the counterexamples to Lagrange.
No.
Because the counterexamples come from quantum anyway to begin with.
Yes.
Okay.
Yes. And in particular, they're all about why there is no submatrix, which corresponds to using like a square or positive polynomial p. But for this structure theorem to hold and to be useful to us, it's enough that p is an arbitrary polynomial, which is non-trivial in the sense that it's not 0. Okay? Any more questions about the structure theorem? Great. So,
Zero, really? That's the only thing you need?
yeah, I'm going to show you.
Oh, because it's normalized by V0.
Yes, yes. So I'm going to show you. So let me show you that this structure theorem is enough to complete our rounding problem, and this is really just a 3 simple observation proof. Okay, here's the proof. First, I want to say that if you look at this reweighted covariance matrix, it's an object that I can touch and feel. Okay, given low degree moments of the distribution mu and given explicit coefficients for the polynomial p, the entries of this matrix are basically linear combinations of low degree moments of the distribution mu, which I had access to. So I can write down this object efficiently. I know that given low degree moments of mu, I can write down this object. Okay, so it's in my hands. That's great. Second, I want to claim that so remember that this is a matrix. I want to claim that this matrix actually lives in the subspace W that I started with. Okay, the reason is very simple. Remember that mu was supported on xs such that xx transpose is in W. That's exactly our polynomial program. All we did is just take a different linear combination of it. Linear combination of rank 1 matrices which are in the subspace is going to give me a matrix which is in the subspace. So far so good. So one way to restate it is to say that if I project this matrix to the orthogonal complement of the subspace W, I get 0. Okay. Now I'm going to use this 2 simple facts to argue that we are done. Okay. In particular, I want to argue that this V0 transpose is a rank 1 matrix which is close to the subspace W that we wanted. So let me prove that to you. So this is the claim that the projection of V0 transpose to the subspace W is 99% of its norm. Okay. So here is simple triangle inequality. The projection's Frobenius norm is at least the Frobenius norm minus the Frobenius norm of the projection to orthogonal complement. So far so good. Now I want to use that the projection of this matrix is actually just exactly equal to 0. So I can add and subtract this without actually any consequences. So here I just add this this matrix that I know is actually 0 when projected to W perp. Yeah, great. And then I'm done because the structure theorem tells me that this matrix here has norms smaller than 0.01 times V0 transpose is Frobenius norm. Projection cannot increase norm. So I get that the norm of projection of V0 transpose to W is at least 99% of its total Frobenius norms. So we agree that if structure theorem is true, we are done. Great. So let's go on to understanding some more intuition about this structure theorem. Let me present one example. Okay, and this would be sort of an illustrative example of, in some sense, how you could think of constructing this reweighting polynomial P. So I want to take my favorite distribution mu. This theorem says that for every distribution mu over the sphere, something should happen. So I'm going to take a specific example of a distribution and see why it has to be true for that distribution. Okay, my distribution mu is going to be basically the uniform distribution on the hypercube rescaled so that every vector in it is actually unit norm. Okay, so in other words, mu is uniform over plus 1 over root n minus 1 over root n to the n. Okay, so if I compute the covariance matrix of this distribution, as you can verify very easily, it is 1 over n times identity. Okay, so far so good. So here's the key idea for analyzing this case, and this actually will be useful in actually even proving the structure theorem in general. Okay, the key idea is to construct polynomial reweightings by conditionings of the distribution mu. Okay, and this is the reason, by the way, why we get positive and square polynomials, and we had the log rank barrier in this approach to proving the structure theorem. Okay, so let me explain how this works. What I will show is the following. I will show that there is a conditioning mu prime of the distribution mu. This conditioning is obtained by taking some event that within mu happens with some large enough probability. I condition mu so that that event happens, and I get the new distribution mu prime, and I actually look at the covariance matrix of the distribution mu prime. Okay, what I will show to you is that this covariance matrix of the conditioned distribution mu prime is approximately rank 1. I want to argue that if this is true, then we actually also can prove that there is a polynomial reweighting of mu which is approximately rank 1. Okay, and the reason is very simple. Basically, the covariance matrix of mu prime is nothing but a covariance matrix of the distribution mu reweighted by a certain polynomial. And let me give you the polynomial explicitly here. So the conditioning I'm going to use is the following simple thing. Let mu prime be the distribution obtained by conditioning mu so that all the first 10 root n coordinates are positive. Okay, they could be both plus 1 over root n or minus 1 over root n. I just fixed them to be plus 1 over root n. All of you agree that the probability of this event is 2 to the minus 10 root n, right? Great. Now my claim is that if I want to write down the conditioned covariance matrix, is the same as a polynomial reweighted covariance matrix of the distribution mu. And the polynomial is basically the rescaled polynomial to have expectation 1, and which this polynomial is basically 0 if any of the first 10 root n coordinates are actually negative. Okay, so all of you agree that there is a 10 root n degree polynomial that will do the job for me. You don't have to like look at this expression, it's basically what you think it is. Okay, and we are done because this is exactly what we wanted. So in particular, if I could analyze and show that this this conditioned covariance matrix is close to rank 1, then I'm done. Right? Great. And one thing I want you to remember as we go ahead in the more general case is that we conditioned on an event of probability to the minus 10 root n, and that corresponded to a reweighting with a polynomial of roughly the same degree, the 10 root n degree. This sort of intuition is important. Great. So now we come to the main claim. Why is the expected covariance matrix of the conditioned distribution close to rank 1? Let me compute it for you. So remember that we fixed 10 root n blocks here to be just fixed to 1 over root n. So if I compute the covariance matrix here, every entry would be 1 over n, right? Because of other coordinates being independent with respect to this block, the cross blocks will actually just be 0, right? And the distribution of the remaining n minus 10 root n bits is basically same as before, uniform. So it will be 1 over n identity. All of you agree that this is the conditioned covariance matrix, right? Great. So if that is true, let me just rewrite it as VV transpose plus this matrix where I have pulled out this block. This block was rank 1, right? So I just pulled out that block and wrote it out separately and wrote out this remaining part of the matrix here. This V, you can convince yourself, is just this vector with 1 over root n as the first 10 root n entries and 0 otherwise. The norm in particular, norm square of this vector V, which is also the Frobenius norm of the rank 1 matrix VV transpose, is just 10 over root n. Again, simple computations. Okay? Now it's simple to argue that basically this VV transpose is basically the rank 1 approximator that we wanted. Why is that? Here is the computation. If you subtract VV transpose from this matrix, the Frobenius norm error is basically the Frobenius norm of this part, right? These are at most n eigenvalues of 1 over n size each. So the Frobenius norm is 1 over root n, or actually less than 1 over root n, right? While the Frobenius norm of the VV transpose part is, as we computed, 10 over root n, which means the error is 10 times smaller than the signal, the VV transpose part, which is exactly what we wanted, right? To summarize, what we did was we started with uniform distribution, we conditioned it, we proved that the conditioned covariance matrix is actually approximately rank 1 in the sense that we want, and then we also observed that conditioned covariance matrix is nothing but a reweighted covariance matrix where the reweighting polynomial is of degree root n.
Wait, where did you get that it's rank 1? How did you get it?
This is what I mean by close to rank 1.
No.
Here is the rank 1 matrix.
That's what you need.
Yes.
But how do you get that?
I proved to you that it is approximately rank 1, right? So what did I do?
You're not doing it in general, you're working through an example?
Yeah.
Oh.
Just an example.
Oh.
Yes, just an example.
Oh, okay.
Yes. So what I told you is for this specific choice of mu, there is a conditioning mu prime on 2 to the minus 10 root n probability event such that the conditioned covariance matrix is approximately rank 1. I showed you that the conditioned covariance matrix of mu prime is same as a reweighted covariance matrix of mu where the reweighting polynomial is degree 10 root n, whatever. Okay? So for the particular case of mu, we are done. You all agree, right? Great.
Do you have a much better polynomial in this case?
No. That's a great question. This is a hard example. For this approach, what I showed you is actually also a lower bound. You can show here that there is no polynomial of degree little o of root n which will accomplish the same goal.
But even if you allow it to be negative?
No, not if I allow it to.
But you don't know, so
I know how to solve this question in log n degree, for example.
You do?
Yes. If the polynomial is allowed to be negative, but if I am doing conditionings, then this is the hard example. Okay?
I see. So is that the general intuition behind this existence of this polynomial? Just that sampling, that root n sampling gives you a good idea of the overall election result?
I would want to say so. Yeah.
The intuition.
Yeah. Yeah, I guess at least in this case it appears like that. Yeah, in some sense, because this is a tight case, I feel, yeah, it's I guess legit to say that this is the intuition. Yes.
Just a sampling.
Yes. Okay. So now let's go on to the general case, proving the structure theorem for all distributions over the unit sphere, right? And of course, somewhere the word Lagrange conjecture that appeared in the title had to show up. This is where it's going to show up. And in fact, the proof will be based on the version of Lagrange conjecture that we know to be true, the root rank theorem. At least I call it the root rank theorem. Okay. So let me show you what this is. So the Lagrange conjecture is a fundamental conjecture in communication complexity. It was made by Lowas and Sachs in 1988. It basically relates communication complexity of a matrix to a certain parameter of some matrix associated with the problem. But I'm not going to describe that version. Okay. Let me describe a version which is an equivalent formulation due to Nissan and Wigderson, which is also sort of more suitable for our application today. Okay. This formulation states just the following simple claim. It says that let's say you take any plus minus 1 valued matrix. So I take any sign matrix. Okay. Say it is of rank at most small n. Okay. And really in some sense you should be thinking of a matrix whose dimensions are exponential in n. So basically you are looking at a really low rank matrix whose entries are signs plus minus 1s. Okay. Then the conjecture states that every such low rank matrix has a monochromatic submatrix, basically a rank 1 submatrix where all entries are plus 1 or minus 1s, and the number of rows or columns in the submatrix is 2 to the minus polylog n fraction of the total number of rows and columns of the matrix. Okay. This of course only makes sense when the matrix is much larger compared to the rank. Is the conjecture clear? Okay, so there has been a ton of work in the past 30 years for understanding and proving and trying to approach the Lagrange conjecture. I'm not going to be able to survey all of that. What I'll tell you is the recent breakthrough to Shahar-Lovett from 3 years ago. Okay, and this is what I call the root rank theorem. What Shahar-Lovett showed is the following: for every plus minus 1 valued matrix of rank small n, there is a monochromatic submatrix, a rank 1 submatrix, whose dimensions, number of rows and columns, is at least 2 to the minus root n fraction of the total number of rows and columns of the original matrix. We wanted a really large submatrix, 2 to the minus polylog n fraction. What we can establish is 2 to the minus root n fraction. Okay, great. So before moving on, I want to give this image because that will help us think about how to apply to our structure theorem. So I want to think of a rank n matrix as basically being indexed by n dimensional vectors on rows and columns, so that the entries of the matrix are just the inner products. Okay, this is just the definition of the matrix being rank small n. Okay, and Lovett's theorem tells us that in any such matrix, so long as the inner products here are plus or minus 1, there is a large submatrix which is rank 1. Okay, great. So let's go ahead and try to see how this is related to the structure theorem. Okay. So let's start with a slightly more general case than before, and this is all I'm going to show you today. Let's say mu is uniform over some choice of capital N vectors, arbitrary but unit. Okay, so v1, v2, v capital N. This is the covariance matrix of this distribution. Okay, 1 over n, sum vi transpose. Let me also write down the gram matrix of this distribution, which is really the matrix of inner products. Again, I and J, so Q is indexed by Q is indexed. The ijth entry of Q is basically the inner product of Vi and Vj rescaled. Okay. Notice that these two matrices are of very different dimensions. This covariance matrix is small n by small n, right? Because X is n dimensional. The vectors Vi's are n dimensional. While this gram matrix is capital N dimensions, the dimensions of it are basically equal to the number of vectors. Despite being this, basic linear algebra shows that they have the exactly same singular value structure. Okay, and this is really easy to verify. Since they have the same singular value structure, it is enough to show that Q is rank 1 or Q is close to rank 1 in order to argue that this matrix is close to rank 1. Okay, so the gram matrix and the rank 1ness of the close to rank 1ness of gram matrix is related to the close to rank 1ness of the covariance matrix. Okay, great. So let me remind you of this picture that I just showed you. This time let's look at this rank 1 matrix as indexed by these vectors v1 through vn that we were looking at, and the entries being inner products. Okay. For a moment, let's assume that Lovett's theorem applied to arbitrary matrices like this, not just the ones that whose entries were plus or minus 1. If that's true, then I could apply Lovett's theorem and say that there is a rank 1 submatrix, right? What would the rank 1 submatrix really mean? It would be a collection of rows and columns such that if I look at that block, it's going to be rank 1, right? So the collection of rows and columns is basically nothing in this matrix but a sub-collection of vectors, because Q is indexed by vectors, right? So what does this mean? It means that if Lovett's theorem, root rank theorem applied to Q, then we'll obtain a subcollection I of vectors. The subcollection would be large because the submatrix is supposed to be large, 2 to the minus root n fraction, such that if I compute the gram matrix or equivalently the covariance matrix of the distribution restricted to this subset, then it's going to be close to rank 1. Okay? So great. In that case, we will just take mu prime to be the conditioning of mu on the event that the vector sample belongs to this set I. And Lovett's theorem implies that the probability of this event happening is 2 to the minus root n. So we are done. We got a conditioning of the distribution mu such that the expected covariance matrix with respect to the conditioned distribution is close to rank 1. Okay? And at this point I want to hand wave the other stuff, which is that if we had this conditioning, we can also build a reweighting polynomial. Okay? Basically, at least you see how it could happen. It's hopefully believable at this point that this could be done. Great. But that basically leaves us with wanting an efficient version of Lovett's theorem that applies to non-Boolean matrices, because our entries were not plus minus 1 in general in our situation. It turns out that there is a very nice proof of Rothfuss of Lovett's theorem, which I really recommend you to read. It's like 3-page long. It's on archive, and it's amazing. It's very, very cute, very, very simple, very, very small. But basically you can take that proof and get inspired from it and develop some iterated version that works to prove the non-Boolean version of Lovett's theorem, which is what we require. So summarizing, we can prove structure theorem using this iterated version of Rothfuss's proof of Lovett's root rank theorem. Okay? Can I again? Yeah, let me take that question offline. Yeah, there are some technical difficulties that arise. We have to take care of those, but okay. Great. So I showed you how to basically do this step 2, right? Remember that our rounding problem was, getting an approximate solution from a distribution. We basically showed that structure theorem was enough. Then I told you how to prove the structure theorem, and therefore we can do step 2. Now we have to go and do the arduous task of trying to dig up what did we really use in our proof. What kind of constraints were important and what kind of constraints could we throw away. Okay? Let me just do like a 5-minute summary of what's going to happen here. Of course, the issue is, the reason we are doing it is because the number of constraints required to actually get a low degree moments of an actual distribution are too large. We can't hope to do that. In fact, this problem of detecting whether the low degree moments of whether certain numbers are low degree moments of a distribution is NP hard. So we can't hope to sort of get this program to be small. But what we're going to do is go and analyze what constraints did we really use as we planned. Okay? So sort of the key philosophical idea, and this is less technical than the key ideas that I told you before, is that if your proof of the rounding was somewhat simple in a certain sense, then replacing the object distribution by a certain version of it which only satisfies a subset of the constraints would be enough for your rounding proof to go through. Okay? And then the hope would be that the number of constraints required is small enough so that you can impose it efficiently. Okay? So let's go and check what did we actually need. This was the slide I showed you for actual distributions, right? In the first step itself, we restricted to looking at only degree root n moments of the distribution. So, and this is the part of the proof I showed you. These 3 steps here. Okay? If you recall, in these steps I used that expectation is linear to argue that the expected covariance matrix is in the subspace W. I of course use that it satisfies the constraints and that it is normalized. Okay, so these 3 things clearly appeared there. And we used these facts only for degree root n polynomials Q because we were only looking at degree root n moments of the distribution mu. It turns out that these 3 things can be captured by just 2 to the root n to the root n constraints. These 3 things are not really a problem now. The issue is what happens with this positivity business. Okay? And this actually is really crucial for the proof. The conditioning based argument that we did, when we go back and look what we used, we utilize the positivity quite crucially. Okay? The key observation is the following. So what we would really want to show is that you don't need positivity for all positive polynomials. That somehow a restricted subset that we can efficiently optimize on is enough. It turns out that this is true. It turns out that we only need positivity for low degree squares, not for all positive polynomials, for only square polynomials. Okay? And it turns out that this is great for us, because if we restrict it to low degree squares, then there is in fact a semi-definite program of n to the O of d size that can compute such an object for us. Okay, this semi-definite program is called the sum of squares algorithm of degree d, which is the second term in the title.
So is this black box or?
Yeah.
So you can go from the structure theorem to this without caring what's in Lovett's or Russell's proof?
Well, like in some sense, it's not like Rothfuss's proof directly applies to prove the structure theorem at the moment. As I said,
if you have a structures theorem, you can forget
yes.
the entire middle part.
Yes.
So this is true regardless of how you got to the
yes.
structure theorem.
Yes. So that's great. This is an object we can actually compute. And a priori you could wonder, so what we really want to do now is basically go and check, is this degree root n version of the distribution object, which we call pseudo distributions, enough for our rounding process to go through. Okay? And a priori you could expect that this could be a tough statement to show. How do I go and dive into where did I use only squares, whatnot, etc. But it turns out that in this, again, we are in very well charted territory. Okay, at least in the past few years, there is a large toolkit of things that we know which help us prove such statements. Okay, and I would point out, I would basically direct you to this website of notes from a seminar that Princeton had last fall, where we have some, some collection of these statements that could be useful to you if you happen to be in this territory. Great, but basically we sort of know how to approach this. This is not sort of a problem that we have to start from scratch. And what we do is we go ahead and actually prove what we wanted here, and then we complete our program by basically writing the convex program that we wrote down before, the degree d sum of squares program where d is root n. Great, so that gives us the full algorithm. Run the sum of squares relaxation, get a polynomial, apply structure theorem, and return whatever vector you get from the structure theorem. So that the algorithm itself is really simple. Once we have all of this, that gives us the main result. So let me spend last 5 minutes in going a little bit vague and speculating about what could happen. As I told before, the main goal of this project when we began was really getting a faster algorithm for small cell expansion, which at this point we haven't been able to do. But and in some sense I want to point out that and other kind of dream theorems that could come out of looking at this problem and extending this approach that we have at the moment. So the first is related to the best separable state or the low rank matrix in the subspace problem, which is to show that there is some log rank like statement that implies a quasi polynomial time algorithm for best separable state problem. This is basically trying to see if there is some reasonable conjecture you could make. As Mark observed before, the log rank conjecture in its present in the form that I wrote before cannot be used here, because for this the 2 to the root n thing is tight. Okay, but the hope is that there is some version of log rank like conjecture which seems reasonable, which implies a quasi polynomial time algorithm for the best separable state problem. This would be a way to ascertain if the Impartliazzo et al. Conjecture can be true. Okay, and I have some candidate variants that we can talk about after the end of the talk. The second is basically the project we started this with. Can we use this kind of rounding idea to get a 2 to 4 norm algorithm or a small cell expansion algorithm? And again, we do have some ideas, but we don't know really how to extend the ideas that we have at the moment. The third is potentially most exciting, at least to me here. And the goal is to show that there is a sub-exponential time algorithm, let's say 2 to the root n time algorithm, that improves upon the approximation guarantee of the Gomans-Williamson algorithm for max cut. Okay? And the reason I believe this could, like the present results could help in achieving this is the following. Basically, you can rephrase the talk I showed you today in order to conclude that you can basically get a solution for the Gomans-Williamson SDP for the max cut problem, where the SDP solution is approximately rank 1 in the same kind of sense that we had in today's talk. So a priori, if we had a SDP solution which is close to rank 1 in trace norm, we would get like a p-tas for max cut. So we don't expect that to be true in sub-exponential time. In some sense, what we have is sort of the best possible version of it. We have something which is approximately rank 1 in a certain norm, The question is, can we use this extra structure of the SDP solution in order to get a rounding which achieves a slightly better approximation than the Goemans-Williamson approximation factor? Okay, so that's basically my 3 dreams for this approach. And thank you so much for your attention.